Hello, everybody. Welcome back. Today we're going to be looking at sort of what I'm calling part 2 of Unit 8.4, which is all about acid-base reactions and buffers. So get your calculators out. We've got a big lesson ahead of us today. I hope you're ready for it, and let's get started. All right, so if you'll recall what we did in the first part of this, my last video, Unit 8.4, the first part, we looked at titration situations between a strong acid and a strong base. What we're going to look at here is what happens when one of those species is weak. And the first situation that we're going to look at is if you have a weak acid being titrated with a strong base. So in this case, the weak acid is our analyte, the strong base is our titrant. Okay, and we're going to just work through a sample problem here where basically, guys, I'm going to show you every possible scenario you could see on the AP exam. So this question says, consider the titration of 100 milliliters of 0.2 molar acetic acid, and then I'm given the Ka value. I know right away that this is a weak acid. Number one, because I know my strong acids, and acetic acid is not one of them. Plus, we're given a Ka value. Only weak acids have Ka values. We're titrating this by 0.1 molar KOH, which I know my strong base is. It's a group 1 hydroxide. Calculate the pH of the resulting solution after the following volumes of KOH have been added. 0, 50, 100, 200, 250. And guys, each one of these additions of base is going to give us a different situation. So that's why I'm working through this massive problem here, okay? But we're going to start this off very much like we did in the last video, which is we're going to look at what are the major species present. And to start this off, 0 means that I have not added any base yet. So let me get to a blank screen here. Okay, so no base has been added. The only major species present are my weak acid, which acetic acid, guys, I'm going to write it like this. Okay, I know that that is not the, official formula for acetic acid, but that is an abbreviation for acetic acid that you'll see frequently. Please notice that I have written the acid together, not ionized into H plus and AC minus. Why did I write it that way? Because it's a weak acid. Weak acids primarily do not dissociate much, so I wrote it together. And I also have water as one of my other major species. And that's it. Those are my only major species to deal with. So when we have not added any base yet, here is my reaction. Okay, and of course, acetic acid is an acid, so when you're predicting products, always come back to simple definitions. What do acids do? They are hydrogen ion donors. So my products here, there's my conjugate base. And here's my conjugate acid. And guys, once you have determined what the reaction is going to be, this is where I use those silly little mnemonic devices. Okay, remember this was one of them, and here was the other one. Okay, and we do different things in different situations. This reaction that I have just written, if you'll notice, has water as one of my reactants. Ladies and gentlemen, this is a Womack's problem, okay? It is not a Newman. So let me erase things here. Okay, this is kind of going back to some things we have done in the past. We're going to do an ice table here. All right, but this is review, ladies and gentlemen. I want you guys to think about, okay, when water is a reactant, remember, this is what that little abbreviation WOMIX. Water is a reactant. We put molarities into the ice table. We'll be adding and subtracting X. We'll solve for X. I want you to go back and look at your old notes if you need to, but I want you to pause the video here and see if you can complete this ice table to solve for the pH. This is old material. This should be review for you. So pause the video, see how you do. All right, let's see how you did. And as I said, this is kind of review material because this is what I called a WOMIX problem. This is something we did towards the beginning of Unit 8. So let's see if you got the right answer. I set up my WOMIX ice table. I was able to solve for X by the way that the method that I used was by graphing the equilibrium expression set up right there. Okay, I solved for the intersection on my graph. I found X, and I knew that whenever I solved for X, that would be equal to the hydronium concentration. And then I was able to plug that number directly into my pH calculation, and I got 2.72. And as I've been telling you all along, ask yourself, does this answer make sense? And it does, because what is it that we have here? We have a weak acid, and that's it. So this pH comes out in the basic range. That makes sense. All right, so let's now move on to 50 milliliters. Now I do have some base on the scene here. So we need to update our list of major species at this point. So let me get to a new slide here. So we still have the weak acid, we still have water, but KOH is a strong base. So I'm going to write that base ionized because that's what strong things do. They ionize, they break apart. So here is my updated list. And ladies and gentlemen, when you have your list of major species, you're always looking for the same thing: acid plus base. Okay, the best choice for the acid in this list, okay, is going to be acetic acid. It's the most acidic thing in that list. The best choice for the base is OH minus. Remember, that is the king daddy of bases. Okay, so for this next part, this is now I've got 50 milliliters of base added. Here is my reaction. Acetic acid plus OH minus. Acids do what acids do. They're going to give away that hydrogen, so I'm going to get AC minus and water. All right, now let's look at this reaction we've just written and let's determine, is this a WOMIX problem or is this a Newman problem? Look at the reactants, ladies and gentlemen. You will notice I don't have water as one of my reactants. So this is not going to be a WOMIX ice table. It's going to be what I call a Newman ice table. That first N stands for neutralization. When we do our ice table here, we're not going to have molarities in the ice table. We're going to have, and this is what that little m here stands for, is we're going to have moles. Or if you watched my last video, I prefer to use millimoles. You don't have to do that, but that's just what I prefer to use. And then when we do our adding and subtracting in our ice table, we're going to add and subtract actual numbers, not X. Okay, so if I need moles, let's go back to the screen here. All right, I have a volume of acid and I have a molarity of the acid. And here's the reason why I like millimoles, because I'm not going to change this volume out of milliliters. I'm going to keep it there. 100 milliliters times 0.2 molar is going to give me, let me come back to my screen where we were. Nope, not that one. Yes, this one. 20 millimoles. Okay. Let's look at the base. All right, here's my volume of base. Here is my molarity of the base. Again, I'm going to keep my volume in milliliters because that just makes things easier for me. 50 times 0.1. Let me get back to that screen. That is 5 millimoles. Okay, we never care about water. Water is the social pariah of the acid-base titration world. Now you might be wondering, am I going to put anything in that position? And here's how you can know, ladies and gentlemen. Look up at our list of major species. Is AC minus, the acetate ion, is that in the list? And the answer is no, it's not. Since it's not in my list of major species, that means initially there is none of it. Whereas look at our reactants, HAC and OH minus, those are in our list of major species, so there is a number there, here and here, because we have some initially present. Now let's review what we do at this point, guys. I'm going to circle OH minus here because I know that it is my limiting reactant, the one that is going to be used up first. I'm going to subtract that number, and on the product side, I'm going to add that number. This is a little bit of review from the last video if you watched it, and that leaves me with 15 millimoles of acetic acid, no base, and 5 millimoles of acetate. Now, what do we do at this point? We're trying to find the pH. Well, ladies and gentlemen, this is really cool. Look at the two species that I have left over here. I have acetic acid and acetate ion. Guess what that is that we're now left with? Dun da da da! We're left with a buffer. Think about the definition of a buffer. I have some weak acid left over and some of its conjugate base. That is by definition a buffer. And guess what, ladies and gentlemen? When you have a buffer, you are permitted to use the Henderson-Hasselbalch equation, which is on your equation sheet. Okay, remember, here's the formula for, I call it the Hendy-Haas equation. Log of base over acid. Okay, well, we were given a Ka value. pKa is nothing more than the negative log of that Ka value plus log of. Okay, now which one of these pieces, acetic acid or the acetate ion, which one is the base in this scenario? That would be AC minus. It's a conjugate base, but it's a base nonetheless. So I'm going to put that one there and this one there. Now, I wonder if some of you are thinking, wait a second. You just put number of millimoles, or if you were working in moles, that's fine, inside that set of parentheses there. Don't brackets mean molarity? Shouldn't you have found those molarities and then plugged them in? Well, guys, guess what? It's not going to end up mattering, because even if I did turn 5 millimoles and 15 millimoles, even if I did turn them into molarities, I would be dividing both of those numbers by the same total volume, and the volume ends up getting canceled out. So it is perfectly okay at this part of the Henderson-Hasselbalch equation, you can plug in moles or millimoles. That is okay. All right, and when we do the math here, this is what we get for the pH. Final answer. All right. Now, look at that pH in comparison to the first step of this problem. We started out at a pH of 2.72. And now look at what it is. It's a little bit higher. Why? Because we added more base. That should make sense to you. Okay, so we did a Newman ice table. We were left with a buffer. Because of that, we were able to use the Henderson-Hasselbalch equation to solve for our pH. So what I want you guys to do is try the next volume here. Now we're going to add 100 milliliters of base. I want you to try that next step on your own. The reaction is going to be the same. The amount of acid is going to be the same. The only thing that will change in your ice table is the amount of base. Okay, but I want you guys to set this one up. Try doing this step on your own. Pause the video, see if you can do it. All right, let's see how you did. So I didn't quite finish this one because I wanted to just talk out a few things with you. So I set up my reaction. I could see that this was going to be a Newman situation. Plugged in millimoles, subtracted the smaller reactant number, ended up again with a buffer. How did I know that? Again, one more time, guys, because what did I have left over? I had some weak acid and some of its conjugate base, which is by definition a buffer, which means that I could use the Henderson-Hasselbalch equation. Now, when I plug in my numbers here, this term right here is just 1. Well, what is the log of 1? The log of 1 is 0. So guess what? This entire term is just 0. So at this point, when we do the math here, we end up with this as our final answer. Okay, and again, if we look back at our last step, this makes sense. The pH is going up a little bit more. Why? Because we've added a little bit more base. Now, this particular step, guys, is a special place in this titration landscape. I want you to focus your attention on this line right here. How much acid did we have? Remember, our acid is the analyte. We had 20 millimoles. How much base have we added? 10 millimoles. We have added enough base to neutralize half of our analyte. We have added enough base to neutralize half. Don't you agree? We've cut it in half of that acid. So ladies and gentlemen, this stage in the titration is special. It has a name, and we talked about this a little bit before. It's called the halfway point, or sometimes they'll call it the half equivalence point. Now there's something unique to this. Now this was not true when we were looking at strong acid plus strong base, but when you put something weak in the mix, there is a special relationship at the halfway point. The pH of your solution at the halfway point will always be equal to the pKa. That is an important thing for you to remember. But guess what? Even if you didn't remember that, you would have figured it out because you'd plug things in and you would see, oh yeah, that whole term is equal to 0. Meaning this whole term is equal to 0, so pH equals pKa. And guys, that will always be true if you're doing a titration with something weak and something strong. Okay? So I want you to write that down. That's an important thing to remember. At the halfway point in a weak titration, pH will always equal pKa. Okay, next step. 200 milliliters of base have been added. I want you guys to try and set this up yourself. It's going to be, one more time, the same reaction, the same amount of acid. What will be different will be the amount of base. Try and set it up, get as far as you can, and if you get stuck, you can come back and we'll work through it. Okay, so pause the video, see if you can get this next step, and even if you can't, we're going to talk it out. All right, I imagine that for this next step, this 200 milliliters of base being added, you were able to get a certain ways, but then weren't really sure what to do. So I imagine most of you were able to get to this point, okay, where I have the same amount of acid and base here. There is no limiting reactant. They both run out, both reactants run out, and all I'm left with is AC minus. So what do we do at this stage? Okay, well, first of all, guys, let's go back to some definitions. Do you remember what it's called within a titration when you have equal amounts of acid and base? We are at the equivalence point. Okay, when your acid and base are both completely consumed, this is where we are. And if you look at what's left at the end of this ice table, I don't have any acid, I don't have any base. The only thing I have left is AC minus, which is a conjugate base. This is not a buffer. I can't use Hendy-Haas to help me get the pH. So what do we do? Well, let's think about what I have left over. I have AC minus, which is a base. It's a weak base, and water. That's it. Those are my major species at this point. So how do you find the pH when you have just a weak base and water and that's it? Well, let's see what that reaction looks like. Oops, let me write that a little better. Ladies and gentlemen, look at the reaction I just wrote. This is a Womack's problem. Okay, and I know this seems kind of crazy, all right, but look at that reaction that I just wrote. Isn't that reaction just the reverse of this one? It's basically that reaction written backwards. But ladies and gentlemen, that is the essence of equilibrium. You take a reaction so far and then it shifts back a little bit. Now, we didn't have to do that in the previous two steps because we had a quick little tool, the Hendy-Haas, to help us find the pH, but you can't always use that because we weren't left with a buffer system. So this is a Womack's ice table. In a Womack's ice table, you need molarities, not moles. Okay, we're not going to worry about water. I don't have any of this. I don't have any of this. I only have AC minus. So I've got to turn this number into a molarity. How do we do that? Well, we're going to divide by the total volume. At this point, ladies and gentlemen, let's think about what that total volume is. I have 200 milliliters of the base, and I had 100 milliliters, if you go back and look at the original slide, 100 milliliters of the acid, so that is 300 total milliliters. Doing this division right here is going to give me a molarity of 0.067 molar. So that is what I'm going to plug in right here. Okay, it's a Womex ice table. Okay, now you do have to be a little bit careful here. AC minus, what is that? It's not an acid, it's a base. So I'm going to say KB equals x squared over 0.067 minus x. And you might say, well, wait. We weren't given a KB value in this problem. We were given a KA. And you're right. But guys, remember, we've used it before. Remember this equation on your equation sheet? You always know this, and we were given the Ka. I can find that Kb value by dividing Kw by the Ka that I was given. Okay, let me erase this, give myself a little bit more room. All right, if we graph this and solve for x, okay, first of all, what is x? You don't have to guess, guys. You wrote it on in your ice table. X is the OH minus concentration. And that gives me a number. If you graphed it correctly, you get something in this neighborhood. Okay. Probably the easiest thing to do would be to find the POH first. So I'm going to plug that in. Negative log of 6.1 times 10 to the negative 6. I get a POH 5.21, okay? But what I'm interested in is the final pH, 14 minus 5.21. I get 8.79. Final answer. Okay, now, whew, that was a lot of work. And I'm not going to lie to you guys. Well, let me say this first. You only have to do these double ice table situations at the equivalence point. Okay, let me say that again. You'll notice that what we have in front of us, we have two ice tables. We did a Newman first. What were we left with? Just some weak base and water, and that's it. So what did we have to do? We had to do a Womex problem to figure out the final pH. You only have to do two ice tables like this if you are at the equivalence point. But in all honesty, guys, many of the AP questions you're going to be asked are going to be at the equivalence point. So it's a lot of work and you're going to be asked about it a lot, but this is what's required, I'm sorry to say. Okay, so our pH at equivalence is 8.79. I want you to think back, if you've watched the last video where we did a strong acid, strong base titration, the pH was exactly 7.0. And that's what it'll always be. If a titration is between strong and strong, look at where this pH is at equivalence. It's above 7. And that should make sense to you. Do we have equal amounts of acid and base? Yes. But are the nature of those species the same? No. Weak acid, strong base. Even though they're the same amount, the base is going to be dominant. All right, it's like having a tug of war where you have 20 members on either end of the rope, but the base team has 20 bodybuilders and the acid team has 20 little kids. Do they have the same number of members? Yes, but the bodybuilders are definitely more dominant. So the pH is above 7. I know that was a lot. Okay, last one, and this one won't take you as long. 250 milliliters of base, same reaction, same amount of acid, different amount of base. See if you can figure this one out on your own. All right, let's check. So I imagine most of you were able to get at least this far, okay? And let's assess the situation. What is it that we're left with here at the end? We're left with some strong base and some conjugate base, and that conjugate base is a weak base. So did you hear that I said the word base twice? At the end of this Newman ice table, I'm left with 2 bases. It's not a buffer, because that's not the definition of a buffer. Do I have to deal with both of these? No, you don't. One of them is much more dominant over the other. Which one is it? Which one is stronger? It is definitely OH minus. That is the king daddy of bases. And I can essentially ignore this other one. So what do we do then? Well, I have a number of moles of OH minus. What I'm going to do is I'm going to turn that into a molarity by dividing by the total volume. So let's think about what that is. There's 250 milliliters of base, and back from the original problem, there's 100 milliliters of acid. So that's 350 milliliters total. So now I have an OH minus concentration. All right, we can find a POH first. That's probably easiest. And let's see what that gives us. Let's see, 1.85. And to get to a pH 14 minus that, here's my final answer. Okay, so what made this step different was the base wasn't my limiting reactant anymore. The acid became my limiting reactant. So what were we left with? We were left with excess strong base, which I could then use to find a POH and finally a pH. So guys, let's go back and just look at what we've done. This was before we had added any base at all. So this is like our starting point. Then we started adding a little bit more base. We started adding base, and we ended up with a buffer. We added a little bit more, still ended up with a buffer, but a very specific place. This was called the halfway point, halfway to the equivalence point. This was at the equivalence point. And then when we got beyond the equivalence point, we were left with excess base. So let's summarize. So at 0 base added, we did a Womix and we used Ka to find the pH. When we started adding a little bit of base, but we had not reached the equivalence point, we did a Newman, and then we were left with a buffer, and we used the Henderson-Hasselbalch. At the equivalence point, we did a Newman, and then we did a second ice table, a Wommack, and we used KB to find the OH minus concentration. Beyond the equivalence point, we did a Newman ice table, and we used our leftover strong base to calculate a POH and then a pH. Okay, now, are you going to have problems on the AP exam where they're going to ask you to do these 5 separate problems? And this took a long time, okay? This is a long problem. And the answer is no, they're not, okay? The AP exam is going to give you questions where they're going to focus in on one of these parts, one of these additions in a titration. The thing is, though, you're not going to know where you are because you haven't done this stepwise addition of base like we just did. The reason I went through all of these scenarios with you is to try and show you all of the possible situations that you could see. Okay, so what would an AP exam question really look like? It's going to look more something like this. All right, so I want you to pause the video, see if you can work through this one on your own, okay? And then we'll go through it and check the answers. All right, so let's check your answers. The first part of this asked you to write the net ionic equation for the reaction, okay? So what I did was I've listed my major species, okay? And remember, we're always looking for what is the best acid in the list, okay, which is HN3. What is the best base in the list? OH minus. And so there is my net ionic equation. Part B said determine the moles of LiOH, and we were given a mass of LiOH. So I just did a little bit of converting here and got 0.025 moles of LiOH. The last part is the solution less than, equal to, or greater, I should say, than a pH of 7. Okay, justify your answer. And guys, you can always use math to justify your answer. So I'll show you my work written out. So I wrote out my net ionic equation at the top of the screen. Okay, this is a Newman ice table. So in this particular problem, since the volume was given to me as 1 liter, I decided to just go ahead and use regular old moles instead of millimoles. And I could see that I was left, at the end of my Newman ice table here, I was left with a buffer, and not just any buffer, but a buffer at the halfway point, because my moles of acid, weak acid, and conjugate base were the same. Okay, so this whole term right there ended up just being crossed out. It equals 0. pH equals pKa at the halfway point. So final answer, my pH of the solution comes out to be below 7, and I've shown that mathematically. So guys, this is, let me go up here. This is more like what an AP exam question is going to look like. It's not, they're not going to ask you to do all those different volume determinations. Okay, they're going to focus in on one part of the titration, but you're not going to know exactly where you are until you do the math and see what kind of an ice table are you dealing with. So the final thing that I want you guys to do, okay, and this is, I'm not going to really talk much at all right, is to do the same type of situation, but the opposite. This time, your analyte is a weak base, ammonia, Your titrant, we're going to be adding progressively more and more strong acid. The process is going to be the same with just a few differences here and there, okay? So I'm not going to talk you through this one, all right? I want you guys to try these on your own. Now, I am going to go through each step and just talk out how I got my answer. But I want you to pause the video and try to do as many of these situations on your own, and then unpause the video to check your answer at each step. All right, so as I said, I want you to try each step one at a time and just see how you did. So here is the first step. All that is there is weak base, ammonia, and water. That's it. So my reaction has water as one of the reactants. This is a Womex ice table. I'm solving for X. I graphed it. X was equal to the OH minus concentration. Don't memorize it. It's there. I found POH first, and then I subtracted the POH from 14, and I get a pH of 11.12. My answer makes sense because all that is present is just a weak base and water. So that pH should definitely be in the basic range. So you guys try the next step. Okay, let's check the next step where now we've started to add a little bit of strong acid, the 20 milliliters. I updated my major species list at the top of the slide. And again, I'm looking for acid plus base. H plus, remember guys, is the king daddy of acid. So that's definitely what I'm going to choose. And ammonia is the strongest base in that list. So I write out my net ionic equation. Based on what I've written, I could see that this was going to be a Newman ice table because water was not one of my reactants. I plugged in millimoles. What I was left with at this point was a buffer. How did I know that? Because look at the two things that we're left with. We were left with weak base and conjugate acid. That is by definition a buffer, which means I can use the Henderson-Hasselbalch equation, which I've written out for you. Now, there's one little difference here. We didn't have to do this in the last problem. Look at the formula for the Henderson-Hasselbalch equation. pH equals pKa. In the problem, we were given the Kb value for ammonia. Well, we've got to turn that into a Ka so we can get the pKa. And so I had to think about this formula, which you can always use. All right, so that's why I did that division right there, because I needed to turn the Kb into a Ka. And my final answer was 9.43. Okay, now let's look at the progress that we've made so far. We started out at a pH of 11.12. We added a little bit of strong acid and the pH has dropped. It should have. So you guys try the next step and we'll check it. Okay, let's check the 25 milliliter addition. Same reaction, same amount of base, different amount of acid this time. Okay, this was once again a Newman, and what I was left with at this point on this line was a buffer, and not just any buffer, a buffer at the halfway point. How did I know that? Because my amount of base and conjugate acid were equal, which means, and even if you didn't realize you're at the halfway point, that's okay, because you would have seen that this whole term cancels out. It equals 0. So at the halfway point here, our pH is 9.25. It's dropped a little bit from where we were on the last step because we've added even more strong acid. So that makes sense. So you guys pause the video, try the next step. All right, this step may have taken you a little bit longer. Whew, there's a lot going on here. Okay, so look at the top of the screen here. Hopefully you were able to recognize that we are at the equivalence point because the amount right here on this particular line, the amount of base and acid is the same. And so at the end of this Newman ice table, I was left with conjugate acid only. It's not a buffer. I can't use Hendy-Haas. So when you're left with conjugate acid only and NH4+, that's a weak acid, the only thing to do is a Womack's ice table. Okay, so what you'll notice here, the reaction that I have written right here is I took that weak acid, NH4+, and reacted it with water. You could have also, on this second reaction here, you could have just written this reaction in reverse. We'll get the same answer. Okay, you can do it either way. But a Womack's ice table, and let me just write that down because I forgot to write that in here. This second step is a Womack's. Remember, needs molarities, not numbers of moles or millimoles. So I had to calculate the molarity of that ammonium ion that was left over. This 150 milliliters, that is the total volume. Because at this point, I have 50 milliliters of added acid, and I originally had 100 milliliters of the base. So that's 150 total. Okay, then I carried out my Womack's ice table down here. Now, how did I know what to put right there? How did I know whether to make this a Ka or a Kb? Because, ladies and gentlemen, what is this thing that is reacting with water? It is a conjugate acid, which is why I set up my equilibrium down here at the bottom of this Womack's ice table with a Ka value, which we were not given. We were given a Kb. So I had to change it into a Ka value. Okay. Then I was able to solve for X, which I could tell from my ice table was equal to H3O plus, and I could use that to solve for the pH. And I want you to look at where the pH at this equivalence point has fallen. It is below 7, and that is where it should be. Let's review. If you're doing a titration between strong acid and strong base, the pH will fall at exactly 7. The last example that we did, where we had weak acid and strong base, the pH at equivalence was above 7. Here we have weak base, strong acid. The acid is going to be more dominant, so the pH falls in the acidic range at equivalence point, below 7. All right, so last step, 100 milliliters of added strong acid. You guys try it. Okay, last part. When we add 100 milliliters of strong base, this time with the way the numbers shake out, the weak base ends up being the limiting reactant. And so what I am left with at the end of this Newman ice table at this level is 2 acids. H plus is a strong acid, and H4 plus is a conjugate weak acid. So because I've got 2 of the same thing left over, I ask myself which one is stronger. It's definitely going to be H plus. So I divided by the total volume, got the H plus concentration, and I was able to find that final pH. So that was a long problem, but I wanted to go through what happens when it's weak base, strong acid. So let's just recap here. When we had not added any acid at all we had was weak base, and we did a Womack's ice table, and we used the Kb to find the pOH and then find the pH. Once we started adding strong acid to that weak base, but we were not yet to the equivalence point, we did a Newman ice table first, and we saw that at the end of that ice table, we were left with a buffer, so we used the Hendy-Haas equation. At the equivalence point, we did a Newman ice table, and then we did a second ice table, but this time it was a Womack's. We used Ka to find the H plus concentration and thus led to the pH. And then beyond the equivalence point, we did a Newman ice table first, and we had leftover strong acid, and we used that to find the pH directly. Whew, that was a lot, okay? But as I said, guys, on the AP exam, are you going to be asked questions where you have to do every single one of those volume additions? And the answer is no, you won't. The AP exam is going to give you questions where they zero in on one of the parts of that titration, but the point is you won't really know where you are until you write out your net ionic equation, write in the numbers, see where you are, okay? The reason I made you go through all of those different scenarios is because I wanted you to see every possible scenario that could come up. Okay, so I know that was a lot of work, but trust me, it will be worth it in the end. So I hope you have learned a lot of something today, and I look forward to seeing you next time.